So we'll start with an open set in the metric topology. So let the set U be open in the metric topology. And let the point X, again using vector notation, being having coordinates x of I, where I is in the set of positive integers, be in the set U. Then, by the previous theorem that we reminded ourselves of, there exists a basis element, which is an open ball in the metric D, centered at x with radius epsilon, such that the point X is in this open ball, centered at x with radius epsilon, which is itself a subset of the set U. Now, we choose a positive integer n such that 1 over n is strictly less than epsilon. And we then let a set V be the product of open balls with the metric rho sub I from, let's start with 1. So rho sub 1 centered at x of 1 epsilon times the open ball under the metric rho sub 2 centered at the point, or the coordinate x of 2 with radius epsilon, and so on up to the open ball under the metric rho sub n for this chosen value of n for the coordinate x of n centered at the coordinate x of n with radius epsilon, and then continue the product to be the entire space x, so starting x of n plus 1 cross x of n plus 2 and so on. So notice that the set V is a product of open sets in the respective sets x of I, where all but a finite number of those open sets are equal to the entire set x itself, x of I itself. So this set V is a basic open set in the product topology. That is, V is a basis element, a basic open set in the product topology. So we'll show that given an element in this set, that it implies that it is in the open ball under the metric D centered at the point X, and which is itself a subset of U, and so V will be a subset of U. So let the point Y, having coordinates y sub I for I in the set of positive integers, be in the set V. Then the coordinate y sub I is in the open ball under the metric rho sub I centered at the coordinate x of I with radius epsilon for values of I from 1 to this positive integer n, and otherwise the point y sub I is definitely in the set x of I for values of I greater than n. So rho sub I from x sub I to the coordinate y sub I is less than epsilon for the values I from 1 to the positive integer n. So if we divide this left-hand side by any positive integer, it's going to be strictly less than this this value, and so we have that the ratio of rho sub I from x sub I to y sub I over I is also less than epsilon, and again for the values of I from 1 to n. Now we'll look at the case where I is greater than n. Now we have that rho sub I, no matter what the points, it's a bounded metric, and so it's less than or equal to 1. So the ratio of rho sub I to I is less than 1 over n, which is strictly less than epsilon, for values of I greater than or equal to n. So no matter the value of I, the ratio of rho sub I to I is always strictly less than epsilon. And so the metric, value of the metric from the point x to the point y, is less than or equal to one of the upper bound, which can be the maximum of any of these values. And so the max of values from rho sub 1, from the point x sub 1 to y sub 1 over 1, up to rho sub n, from the point x sub n to y sub n, divided by n, or for values of the index I greater than n, always less than or equal to 1 over n, which, again, each of these values is always strictly less than epsilon. And so we have that the distance under the metric capital D from point x to the point y is strictly less than epsilon. And so the point y is in the open ball, is in the set V. Again, is in the open ball under the metric D, centered at the point x with radius epsilon. And so we have demonstrated that the set V is a subset of the open ball under the metric capital D, centered at x with radius epsilon, which is itself a subset of the set U. So, in other words, we started with the set U that is open in the metric topology. We have that for every point x in the set U, there exists a basis element V in the product topology such that that point x is in the set V, which is a subset of the set U. And so the set U is open in the product topology. So we have demonstrated that every open set in the metric topology is also an open set in the product topology. So now we need to show the converse. So conversely, let the set U be open in the product topology. Then the set U is a product, a countable product of sets U sub I, where U sub I is open in the space X sub I for every index I, and U sub I is in fact equal to the entire space X sub I for all but finitely many values of the index I, and we will call these values alpha 1 through alpha 2, or correction, alpha sub n. So, given a point x with coordinates x sub I in the set U for each index, the coordinate x sub I, is in the set u sub I, where u sub I is open in its respective topological space. So, for every index I, there exists an open ball with under the metric rho sub I, centered at that coordinate x sub I, with radius epsilon sub I, so we allow for the radius to be different in each respective topological space, such that the coordinate x sub I is in the open ball under the metric rho sub I, centered at the coordinate x sub I with radius epsilon sub I, which is itself a subset of the open set u sub I. So let the set V be the countable product of sets V sub I, where V sub I is the open ball under the metric rho sub I, centered at x sub I with radius epsilon sub I, for values of I that are equal to the given values alpha 1 through alpha n, and V sub I is the entire space x sub I for all other values. Of the index I. Then the set V is a subset of the set U, since for every index I, V sub I is a subset of U sub I. So now define the number epsilon to be the smaller of the values of the ratio of epsilon sub I to I, for the values of I being these values alpha 1 through alpha n. Then the open ball under the metric big D, centered at the point X with radius epsilon as just defined, is a basis element in the in the metric topology on the countable product space. So we'll show that given a point in this open ball, that it implies that it is in the set V, which is itself a subset of the set U, and so the open ball will be a subset of U. So let the point Y with coordinates y sub I be in the open ball. Then the distance under the metric big D from the point X to the point Y is less than epsilon. And so for every index I, we have that rho sub I from the coordinate x sub I to the coordinate y sub I over I is less than epsilon. In particular, if the values of I are those given values alpha 1 through alpha n, then rho sub I from x sub I to y sub I over I is less than epsilon sub I over I, so that rho sub I from the point x sub I to y sub I is less than epsilon sub I. So for these values of the index I, being alpha 1 through alpha n, the distance from x sub I to y sub I is less than epsilon sub I. So the point y sub I is in the open ball under the metric rho sub I with radius epsilon sub I, and otherwise for all other values of I is in the entire space x sub I. And so we have that the point y is in the set V, and we have demonstrated that the open ball under the metric D centered at the point X with radius epsilon is a subset of the set V, which is itself a subset of the set U. So in other words, for every point X in the set U, there exists a basis element which is the open ball under the metric D, big D, centered at X with radius epsilon, such that the point X is in this open ball, which is a subset of the set U. And so the set U is open in the metric topology. On the countable product space. So we have demonstrated that every open set in the metric topology is also open in the product topology, and conversely that every open set in the product topology is also open in the metric topology. And so the topology induced by the metric big D is the same as the product topology. On the countable product space. Okay, so notice that this theorem states that the countable product of metric spaces is metrizable. And in fact, the metric capital D induces the product topology. Another thing to take note of is that as each space X sub I is a metric space, the product, the countable product of these spaces is Hausdorff, as it is the product of Hausdorff spaces, as each metric space is Hausdorff. Okay, so we will end here for today. Next time we'll continue to study metric spaces and look in particular at real spaces. We'll look at a new definition of continuity that is only valid in the context of a metric space, and we'll begin to look at the concept of a complete metric space. So I hope you have enjoyed the 17th lecture. Thanks for watching.